Okay, now it started. So if you're just joining us, we just took the quiz. Here's the quiz. You can pause at this point if you want to try it. Now let me show you what I did. I've got it over here. So first things first. Oh, it's paused. Got to unfreeze this. Yeah, they saw. Don't worry. Um, so here's what I started with: is I got my rectangle. Hopefully, I saw a lot of good rectangles, something like this. And then you've got to figure out where these things intersect. And so you set those equal to one another and do some algebra. This one is kind of like intermediate algebra. I wouldn't call it basic, but it's not terrible. So here's how I did this. I set those equal to one another, and then I moved the 3x over to the left. Some of you might have canceled the x, which I guess is okay as long as you recognize that 0 is a solution. But anyway, I moved it over to the left, and then I got this here, factored out the x equals 0, or this stuff equals 0. And if you take the right-hand side and do a little bit of manipulation, you get that x is equal to plus or minus 2. So squared everything, and there it is. So plus or minus 2. That's why I had to specify the fact that we're in the first quadrant, because this thing, it actually, the cubic, or it's not a cubic. What is it? It's the square root of a cubic. Yeah, if you multiply through. But anyway, whatever it is, it's symmetric. You end up with another branch that goes down here. And so I wanted to specify that I'm interested in this portion up here. So there it is. So it's basically, this is 2. So if you were going to set this up with no other work, you'd at least get half credit. You should have something that looks like this. So down here, I'll move it up in just a sec. But you've got your limits, 0 to 2. The top minus the bottom. That's what we're looking for. Top minus bottom, dx. But, once you have that, now the problem of doing the integral, and here's where the substitution comes in. I broke this into 2 separate integrals just because I didn't want to have to deal with substituting over here. So that integral is easy, of course. This one is the substitution thing. So I went through the trouble of doing the substitution. And as I mentioned, every time I do substitution, I'm going to, first of all, rearrange my expression so that I have du. And that's where this 1/2 comes from. The 1/2 doesn't magically appear. And it's like, I think I mentioned this last time, that when you're substituting, you don't just put the 1/2 there just because there's a 2 somewhere. The 1/2 is because I want this to balance. Over here, there's no coefficient. So 1/2 times 2 is equal to 1, which is what I want. So don't just, don't think of this as some sort of a magic trick. It's not. It's algebra. Although algebra does feel like magic sometimes. Anyway, after the substitution, this is straightforward. Plugging in, I got this after doing the antiderivative, and then I resubstituted, and I have my limits back there. The rest of this is pretty straightforward, though, so that you have this. Oh, sorry. I guess I had oh, come on. Why is it doing this? There we go. Let me try again. Let's get rid of that. There. It's minus, that minus. So I did my antiderivatives. I think I was just so excited to have done the antiderivative that I forgot to put the minus there, but I got it here. So I have 6 minus 9 minus radical 5 over 3. You could do this on your calculator. That works. This works. If you were too lazy to simplify things, I'm fine with that, at least to some extent. So if you wrote it as, I don't know, some of you might have written this 1/3 times 4 plus 5 times, I don't know, to the third. I don't know. You could probably come up with some crazy way to write this, which doesn't look at all correct, but it might be. Okay, let's move on. So just a little bit more practice with this. If you're still having trouble with either of these ideas, either coming up with the area or doing substitution, please do seek out help either from myself or from Center for Student Success. Hayden. Excellent. He realized that's the best way of doing it. Sometimes it just has, it helps to talk through something with someone. So, or just talk through it with yourself. Okay, let's move on. We're going to be doing volumes today. And we started this last time. Just to remind you what we did, we had index cards. We were imagining rotating them around an axis. And then I pointed out that that's just, this is a stand-in for other problems. So this is not all that important, I should say. I don't know if I should say it that way, but it's just a stepping stone to understanding the process of doing what we're doing. Okay, so today we're going to be looking at solids that are made by rotating a curve around an axis like this. So you have a curve. Let's have this go away again. There it is. So you have this curve, rotate this around this axis, and you get a solid. So this is, I showed you these before. This is this curve. You can kind of see it on the back here, rotate it around this axis, and you get this solid. I've got some other ones here. Here's a curve. It's a little harder to see, but these are just to demonstrate that these are discs. But you can see that there's a curve. This is actually the square root of x, I guess, would be what this is, rotated around the x-axis. But you could take this apart and observe that these are actually disks. And if we find the volume of all the disks, add them up, we'll have approximately the volume of the solid. So that's the goal here. By the way, we're not going to stop at disks. Today we're going to do disks, and we're going to also do this one here. So this one is a sine and a cosine curve. You can kind of see them on the back, the cosine on top, the sine curve on the bottom. And I've rotated that area around the x-axis, and it produces this thing with a hole in the middle of it. So if I were to take each of these ribs, and if I were to separate them from this piece of plastic, each one would be more like a washer than a disc because it has a hole in it. So it would be more like this object. So this is what we used to. These, by the way, things like this cost like $100. This costs like 50 cents because I just printed out of plastic. No, probably more like $1. But anyway, so yeah, this is all we had back in the olden days. But anyway, you can see this is a washer. It's got a hole in the middle of it. So if I take this object and slice it this way, then I'm going to end up with these washers. And I'm going to have to find the volume of a washer instead of a disc. But the process is almost the same. So let's go ahead and do this. Remind you of the volume of a disc. So a disc, we're going to call this, at least temporarily, delta x. This is going to be, let's just call it, I'm going to call it h because that may vary how h is not a good thing to use for this, is it? Let me get rid of h and I'll just call it f of x. Okay, so pi times r, which is f of x squared. So this is the volume of this thing, times delta x. So this is the structure that our things are going to fall, it's going to look like this, but I need to warn you that it's not always f of x that we have in there that's squared. What's important is it's the distance from the axis of rotation. That's what goes in parentheses here. And so maybe it would be helpful if we started off with a problem. Let's see, yes. Let's start off with letter B here. Let's do letter B. So for this disk method example. So in fact, I'm going to just switch over to Notability so that I can draw this a little bit better. So y equals 2x squared. What were just a minute. Y equals 0, x equals 2. Y equals 0, x equals 2, and I want to rotate around the line x equals 2. So this is different from all these things that I've shown you already, but I want to do a hard one first, then we'll do the easy one. We'll do the same thing, but with a much easier version in just a sec. So first things first, with all of these, you have to sketch your diagram. So what does 2x squared look like? It's a parabola. Technically, it's a little steeper than this, but I'm just going to fudge a little bit, make it a little bit easier on myself. Here is the line x equals 1, or x equals 2, sorry. X equals 2, y equals 0 is the x-axis. And so the region that I'm interested in is this region in here, this sort of weird wedge. There it is. Okay, so now let's talk about what this is going to look like. I'm going to rotate around the line x equals 2. So let me draw the axis of rotation here. So that's the line x equals 2. And I'm rotating around that. So you can imagine that when I do this, I'm going to end up with some disks. So here there's going to be a disk, and then here so I'm going to have a stack of these disks that get bigger as you go down. So the top, it's going to be a really little disk, like this little disk up here, and then when you get down to the bottom, you're going to have a really big disk. But they're all disks. They're all going to be disks. They're solid. They don't, even though these do have holes in the middle, those will not. So these are disks, and I need to know what these are going to look like. Well, let's draw on a representative rectangle, and I know that this will be disheartening for you because on this first example, I have delta y as my small side of this rectangle. I'm going to take my time with this one. Don't worry. Let me redraw this. Okay, so I've got this. And imagine that this thing turns into this disk. So we know the height of the disk is delta y. But what about the radius of the disk? So the radius of the disk is the distance from the center out to the edge of the disk. It's this. That's the radius. So how would you describe that? So take a minute and answer the question, and don't worry if it's wrong. It's just, let's see where we are with this. What would be the distance between here and here? How would you compute that? Take a minute and jot something down. And I'm going to pick some people out, not to embarrass anyone or to, oops, just a sec. But I just need some answers. And I am completely expecting the answers to be wrong. So if you get the wrong answer, I'll be appreciative of that effort. So Caleb, what do you think? What is R? And if you want to give me the right answer, that's fine. But I'd prefer a wrong answer. What do you got? So it's like the distance between, so are you measuring in the x direction or the y direction? The x direction, right? Okay, so what's the x value here? 2, okay. So I'm going to start with 2, right? So we're going to start with a 2 minus something. So basically it's going to be 2 minus whatever this is. Okay, it's a good start. So 2 minus whatever this is right here. Now the problem with that point is that as you go up and down, the 2 doesn't change. It's always 2. The problem is that changes. So I need to be able to express what that is. And so let's see, I'll get someone else to join the fun here. So Carson, what do you think? What am I gonna put there? 2 minus what? Okay, 2 minus 2x squared. That's a good guess. So I'm going to put this in sort of let's see, brackets here because it's not right. But he followed the instructions. I told him to give me the wrong answer. Thank you, Carson. So that's a common wrong answer though. So but I like the way Carson is thinking. See what you're thinking. Don't write that down. And we're gonna change that out in just a minute. You see, what Carson is thinking and what I would be thinking if I were Carson is I need to know the difference between here and here. And this is this red line, right? This red curve. And then I think, well, what is the red curve? The red curve is y is equal to 2x squared. True? So this is great. He's identified the correct place. The only problem is that I need an x value, not a y value. You see, y is equal to 2x squared, and 2x squared is actually the distance up and down, 2x squared, from the ground up to that point. So that's the issue there, but it's a good start. So 2x squared, that's how high this is. I need to know how far you are over here. And so to do that, I'm just going to rearrange this expression. So let me get rid of this just briefly. Technically, what you're doing is you're actually doing this. This distance here is the value x. So what I could do is I could take this and rearrange it and solve for x. Y over 2 is equal to x squared, which means that x is the square root of y over 2. And that's the right thing to do. So notice that my distance, now there's a couple of, here I'll give you some hints because I know that this is so confusing because you're used to thinking of functions of x, and so that's why I thought, let's do the hard one, and then we'll back up and we'll do the easy one. The easy one is going to be a breeze after this. But anyway, so this hard one, we're looking for this distance from the y-axis over to here, and that happens to be the value is x, but I need to write it in terms of y. Now, here's the other thing to note, is because this is delta y, when I get to the point where I'm going to write a summation and an integral, the summation will have delta y in it, and the integral will have dy in it. And so I need whatever is here to be in terms of y, not x. So this is why when Carson said 2x squared, that might be what you thought too. You were so close. You're right. You're right. We need that function, but we need to write it in terms of y, not in terms of x. So just shift the focus a little bit and you'll get the right answer. Anyway, let's actually figure out what this volume is. Now that I've got the correct radius, I need the volume of this disk. So write down what you think the volume is based on this information here. We'll see how you did. Michael G., you got a volume, don't you? All right, take your time. Yeah, what's up, Emily?
So, if that expression for the radius that we just found, so it's 2 minus our equation in terms of y. Is that the diameter, not the radius? Because that's like all the way across, right?
Well, on the picture here, it's the distance between this point right there and this point right here.
Right, but is that like all the way across the circle?
No, because what's going to happen is we're going to be rotating. We're going to revolve this thing.
Oh, I see.
So this thing goes around, and so you'll end up, that point will end up over here. So yeah, it's just the radius. Yeah. Oh, it's so hard, isn't it? All right, Michael, do you have our volume?
Yeah. It would be pi parentheses 2 minus square root of y over 2 parentheses squared delta x.
Delta y, you mean?
Oh, yeah.
Yeah, this is a delta y. Very nice. So volume is pi r squared h. So pi times the radius squared times the thickness. Very nice. And so now I'm just going to rewrite this like this. 2 minus radical y over 2 squared times delta y. That's my, when I add up all of these disks, when I add them all up, I'll have this for my volume. And then I do a limit as delta y goes to 0, and I get this. So this will be the integral. Oh, we need limits though. We'll get them. 2 minus the radical y over 2 squared. Okay, I need my limits. So let's see, where are the limits? The limits will be in terms of y, not in terms of x. So my limits will be starting down here. That's easy enough. That's y equals 0. And ending up there, y equals, wonder what that is. Well, let's find out. I need to figure out what y is when x is 2. Well, look, I've got an equation right here. So y is equal to 2 times 2 squared, which is 8. So that's y equals 8. So you can see I am not drawing to scale for sure, because this thing has been squished down quite a bit, but it gives you a general sort of idea of what this shape is going to look like. By the way, when we get done, yeah, what do you think? Oh, yeah. Look at that. I made the, yeah, that's a classic rookie mistake is I put the X there instead of the Y. Yeah, this is all in terms of Y, so my value should be Y. By the way, let me just show you what this thing looks like for real. So for real, what it would look like is more like this. Okay, that's a little bit better. So it's a very tall, skinny region. And if you were to rotate this around this axis, what you're going to have is it's going to look like a long, one of these things that they play like a trumpet, but it's just straight. I don't know what you call it. No, not a trombone. Yeah, you know, like I don't know, not even, yeah, like in that classic Robin Hood, what is it, by Disney, the Disney classic Robin Hood from the 60s, where they have the, I don't know, the hippopotamuses that are playing their long, whatever, trumpets. Yeah, anyway, it'll look like this. Here, there, that's what I mean. And you could have put a flag off of this and says math. Okay, whatever. Okay, that's what I just wanted to give you a visual for what we're thinking about here. Okay, so this has been squished down considerably. Okay, so now all we have to do is compute that. That is kind of a pain. I'll do it relatively quickly, I guess. Let me pull the pi outside. 0 to 8. I need to square this thing. So this is going to be 4 minus 4 times radical y over 2 plus y over 2. Okay, so I'm not going to do this fully. I just wanted to show you that you would expand that, do the algebra, and then this even, I would write that as 4 over radical 2 times y to the 1/2. And this, of course, is just 1/2 y. So then you just do term by term, easy integral that we can do. So not too bad. Maybe while you're working on the next problem, I will go ahead and compute this just so that we know what number we're dealing with here. Because your next job is to do the same thing, but instead of rotating around this line, you're going to do the easier thing and rotate around this line. So the horizontal axis. So that'll be much easier. Give me a sec. I'm going to put this back up here just so you can see. This is part A now. We're going to rotate around the x-axis. And so what I will, oops, that's not what I want. I want this. So give me a sec. I'm just going to copy this so that we can redo this. Hold on a minute. Copy. And so your job is to set up, here just a minute. I'm going to get rid of the stuff that we don't need. Hold on a minute. Almost done. Okay, I think that gets rid of almost everything that we don't need. Oh, up there. We don't need this. We don't need this. Okay, so your new job, same region, but we're going to rotate around the x-axis. So here's how this is going to look. And so my rectangle, this is going to be much easier. My rectangle will be this. So there it is, delta x. So here's your job is, first of all, sketch as best you can. By the way you sketch a disk is draw an oval, like I've done, so a stretched out circle, and then draw lines on the top, and then do your best to try to make this curve is close to the same as the previous one. There we go. Okay, so there it is. So here, how big is that? How big is this? And then come up with the volume of the disk. Once you have the volume of the disk, we're going to write this as a summation and then as an integral. This one is going to be far easier. And while you're doing that, I'm just going to get the value of the integral that we just did. Just because I'm curious. See, I'll freeze so you don't have to see all my mess here. That way we can compare. It's kind of fun. Okay. All right. I used my computer. I cheated, but it's okay. All right, let's see where we are. Certainly you could at least get this first bit down. There we go. So, so let's fill in the diagram first. So Emily, what is the radius of this disk right here?
It's just the y value, so it's 2x squared.
Very nice. So in this case, your intuition about that first one, I told you I was doing the first one first because it's the hard one, and everyone, if you did this one first, you would assume it was always like this. But yeah, so here it's just 2x squared. It's just this height. As this thing rotates around, that is going to be the radius. Very nice. The thickness, of course, is delta x. Delta x. Now we need to come up with the volume using the Americo knows the volume, don't you? You know the volume of a disk, though. What's the, in terms of R and H or whatever? Pi r squared times the thickness, right? All right, so what's the R here? 2x squared, good. And then how thick is this disk? All right, there it is. So there's my volume for this one disk. Perfect. And now we'll just put this into the summation formula. It's kind of extra, I guess, to do this, but I'm going to anyway. Delta x. And then, of course, you're going to set this up as an integral because we're doing the limit as delta x goes to 0. And your limits here are from 0 to 2. This one was far easier. X equals 0 to x equals 2 is the region. So there's the integral. See how easy that one was? So most of them hopefully will be this easy, but every now and then you'll have something that's a little bit more challenging. Oh, here, clean this up a bit more, and then we'll get someone to help me out. So this will be 4 pi times the integral from 0 to 2 of x to the 4th dx. Does that look all right? All right, let's do this antiderivative. Hunter, what's the antiderivative of x to the 4th? Beautiful, 4 pi x to the 5th over 5 evaluated from 0 to 2. Very nice. And then we just have to plug this in. So I guess I'll just do it. 32. 32 times 4 is 128. So it's going to be 128 pi over 5. 5, sorry. 5. Okay, if you're curious which way is bigger, so you can imagine if I were to rotate this, let's see, this is what it's going to look like. This big thing here. Okay, that's not even right. But rotating around the x-axis, you end up with this, not really a trumpet. It's this huge, like really flat squish thing. It won't look nice like my math trumpet. But this is the, I did that one up there. This is the rotating around the line x equals 2. Gave me that volume, 16 pi over 3. And then here's the volume of the other way, is 128 pi over 5, which I believe is bigger than 16 pi over 3. I'd have to compute the decimal, but I'm pretty sure that that's, well, let me think. 125 is over 5 is 25. So that's about 25 pi. And this one is about 5 pi. Yeah, so we're off by about a factor of 5 times bigger. Okay, we need to move on though. So what happens if you have something like this? So this situation, let's see, I'll just write down, we'll just use this one. This one's much more fun. Hold on a minute. I have some examples here, but let's just switch back to here. So we'll use this big yellow thing. Sorry if you're watching the video, you can't see. But we have, let's see, y is equal to 2 cosine of x, and y is equal to, oh, I'm sorry. No, that's not right. Sorry, I think some stuff has rubbed off. Let me try again. It looks like it's 3 plus 3 cosine of x is that, and then that has to be 3 plus sine of x. Yeah, that looks right. Hopefully that's right. Yeah, some of the filament has come off of my thing here. Yes, I'm gonna need to reprint that. But we get the picture. So let's see if I can. Is that right? Hold on a sec. Yeah, I think that's right. Let's see if this works out. So first of all, I'll graph this thing. And here's what I get. Whoops, I did that wrong. Okay, so here's 3, here's 6. Okay, so 3 plus 3 cosine of x looks something like this. Negative pi over 2 will go. Yeah. It dips down like this, but I think we're going to be done right there. Okay, then 3 plus sine of x. So 3 plus sine of x. Yeah, this is not going to be what it's not the same. This must not be the same object. You know, let's do it this way then. I'm going to cheat. Put a 2 in there. I know. That way it'll intersect where I want it to. So this looks like this. There. There. Now it intersects. Now it looks like what I have here. I don't know what's going on with those functions, but this will at least give us the picture that I want. And that's this picture right here. I'm going to rotate this around the x-axis. So you can see what's going to happen is when I rotate this around, I'm going to end up with a disk. So this is a delta x here. This disk has a hole in it. So you get this washer. So it's like this right here. So the thickness, the process that we're going to go through is almost the same. It's just an additional complication of having the hole in the middle. But the hole in the middle isn't that big of a deal. The hole in the middle just means you take the volume of the outer disk and then subtract off the volume of the inner disk. Let me just find one that's about the right size. There we go. So you have the solid disk here. You have the volume of the whole thing and subtract off the volume of the inside disk. That's it. So that's all that's going to happen here. So let me go ahead and with this picture, see if I can indicate everything that I need to. So first things first, from the middle to the outside, that is going to be 3 plus 3 cosine of x. So notice that would be this on the diagram. It's from the x-axis. By the way, anytime you rotate around either the x or y-axis, you should be happy because you don't have to do hard math in terms of setting up these things. If you're rotating around an axis that is not the y or x-axis, then you have to think about, subtracting like we did up here. How far are we away? What's the radius? So that's where things are going to be hard. This is easy though. So we'll do an easy one first. And then if we have, well, we aren't going to have time. So we're just going to do an easy one, and then we're going to see how things go. Okay, let's see. What about the inner circle? This inner circle is the same as this curve, and that ends up being 3 plus sine of 2x. All right, now what we're going to do is we're going to set this thing up, the volume. And I would suggest you do it this way. We have the volume of the outer circle, the outer disk is pi. Oops, I'm going to color code this. Is pi times the radius squared times delta x. That's the outside circle. And then the inside circle is going to be subtracted from this, pi, just a sec, let's move that over a little bit, times the inside circle squared delta x. So you have the outer circle, the outer disk, and the inner circle, or the inner disk. Let's set this up. We're not going to do this fully because of a little issue that we're going to have with the actual doing the antiderivative that I'll mention. But so the way I would set this up is I have the integral from negative pi over 2 to pi over 2 of pi times 3 plus 3 cosine of x squared dx minus the integral from negative pi over 2 to 2, pi over 2, sorry, of pi times 3 plus sine of 2x squared. So this is the most important part, is setting this thing up. And we aren't going to be able to do this integral because we don't have the techniques that we need at this point. But at least hopefully you see how it's set up. Let's just set up one more, because it would be nice to have one that's set up, even though we don't have time to do it fully in 4 minutes, have one that is set up that you could do. So let me show you what I mean by this. So let's change gears. Let's rotate. Rotate. We're going to go y equals, let's see, 1 minus x squared, y equals 0. So that's what we're rotating around the line y equals 2. So let me just set this up in the next 3 minutes. So step 1 is draw this. 1 minus x squared, hopefully this isn't too difficult for you to figure out. Y equals 0, you know where that is. So we're talking about this region. And I picked numbers that were easy enough that hopefully this won't shock you, is that this is negative 1 and this here is 1. So that's the region. Now for the sad part, we're rotating this around the line y equals 2, which means that you're going to take that thing and sort of rotate it all the way up and around. So bear with me. We're going to put a rectangle in here. And then imagine rotating that rectangle around that line. Here's sort of the line there. And it has a hole in it. There we go. So this is y equals 2. And I'm going to need to know the following. This distance here, which corresponds with that red arrow. And then this distance that goes all the way to the edge, that corresponds with this dark blue arrow. So you see how it's going to be more complicated, but we can do this. So I think that we probably can all figure out the dark blue arrow is always going to be 2. You see that that's always 2 no matter where you are. Move this purple rectangle left and right. The dark blue, you're always 2 units up and down. The top one, the red arrow, is a little bit harder, but we can do that. That's going to be 2 minus the height of this purple thing. And the height of the purple thing is 1 minus x squared. Here, this thing is 1 minus x squared. So yeah, I know it's really difficult, confusing, but take your time. You'll be able to do this. Let me just write the volume down, because once you have the volume, you can do the rest. So the volume of this thing is going to be pi times 2 squared times delta x. Sorry, I put the delta x there, minus pi times that red thing squared times delta x. So hopefully you can see how you can take that, put it together with the limits to come up with an integral. And this is a polynomial. This we could actually do, unlike the sine and cosine. Sine and cosine we'll be able to do in a couple of weeks, but not now. So you're going to be, this will be like your homework. Hopefully your homework will be relatively doable. Whew. Okay, so this is hard stuff. I know it took us 2 class days to go over this. Do your best to try this out. We'll hopefully be able to do things on Monday after you've tried this.